Einstein's classical theory of space-time curvature, relativity, general theory of relativity. Why do you, if you combine that with quantum mechanics, which is what people say you should do, why doesn't that also provide a kind of symmetrical theory? And it doesn't really answer this question. So the scheme that I'm going to describe, and those of you who heard me, some of you may have heard me talk about these things 3 years ago. It's the same scheme as I was talking about 3 years ago, if you remember it, if you were here and remember it. But I have some new developments which I want to talk about. But let me say something about black holes in the remote future. Suppose you have a black hole. Well, here is what you would expect ultimately. See, this is the picture I had before, basically. Collapsing material, and there's your black hole, and here are your light cones telling you how things propagate into the future. Now, black holes, according to Stephen Hawking, have a temperature. They not only have a very high entropy, and you remember in my previous picture here, I had a black hole representing the sort of high stable entropy that these things in the box would tend to reach, and that representing an enormous increase in the entropy. And this is the Bekenstein-Hawking formula for the entropy is what gives you this value for the entropy. I should explain that the universe as we know it now, by far the largest amount of entropy, or randomness, is in black holes. Our own galaxy contains a black hole which is roughly 4 million times the mass of the sun. It's a huge black hole, 4 million times the mass of the sun, and it represents easily the greatest amount of entropy in our galaxy. It seems to be the case that galaxies generally do have black holes in their centers, and relative to the sorts of things that we see somewhere, ours is a relatively small one. I think the record at the moment is something like 10 to the power 10 solar mass black hole, whereas the 4 times 10 to the 6 is our one, you see, so it's a lot bigger than the black hole in our galactic center. Now, according to Stephen Hawking, not only do you have the entropy from the formula which Bekenstein originally suggested and then Hawking refined, but there has to be temperature going along with it. So the black hole is not entirely cold. It's very cold, but not completely cold. It has a temperature. The highest temperature of any black hole that we have any reason to believe in the universe would be for the smallest black holes that are out there. The bigger ones are colder. The smallest black holes out there, something of a few times the mass of the sun, would have a temperature which is roughly the same as the coldest temperature ever made on the Earth. So you have to think of something pretty cold, and so the radiation which is associated with this will be so teeny that it's hardly worth worrying about. However, as the universe expands, and it undergoes that exponential expansion in particular, and I refer to over there, the temperature goes down and down and down, and then the temperature of the universe, the microwave background, goes down to a temperature which will be less than this coldest temperature ever made on the Earth. It will get a lot less than that, and it needs to get a lot less than that. So the very big black holes that are there, but then they will become the hottest things around. And then when they're the hottest things around, they will start to radiate away, photons coming off, and these photons will carry energy and therefore mass away from the black hole, and the black hole will then start to shrink, get smaller and smaller and smaller. This is the Hawking evaporation of a black hole. I have to say that this is an awful long time. I've put up to 10 to the 100 years. For the largest black holes that we expect to arise in galactic clusters, you have to think sort of in terms of what we sometimes call the Google years. 10 with 1 to be followed by 100 zeros, which is an incredible length of time. Our own age of the universe is only 1.4 times 10 to the 10 years since the Big Bang. So here we have 10 to 100 years. That's an awful long time. But eventually, these things will disappear with a pop. I'm calling it a pop and not a bang, because although if it went off in this room, it would be pretty unpleasant and probably kill several of us. It's not big from the point of view of cosmology. In fact, it's ridiculously small. In fact, this was one of the things which started off the kind of scheme I was going to describe to you, was the thought that the most exciting thing left when the universe is doing all this expansion is waiting for these black holes to go off pop. And it seems to me that was a pretty boring thing. I could hardly think of anything more boring than waiting for the black holes to go off pop. Here, you see. That's the boring era, but after that is a very boring era. There aren't even any black holes there to go off pop. And it did seem to me like this is an emotional argument, and I agree it's an emotional argument. I have nothing wrong with using emotional arguments in science if you eventually back them up with hard facts. If you want to be guided in some direction, okay. So I was certainly guided in the direction that I'm going to describe in a moment, which was this very boring era. It seemed to be such a miserable end for this exciting universe that we seem to be living in here, where we're around here. Well, this isn't to scale, I should say, of course. This has got to be tens of 100 years. But I had to cheat in this picture to be able to get the pops in. But there we go. And okay, that's a pretty boring universe for most of the time. And it seems to be a bit sad end for this exciting universe of ours. But then I began to think, well, you know, who's going to be around to be bored by this universe? Well, not us. The only things that are going to be bored around are more like photons. So here they've been coming out of the black hole, and you'll have lots and lots of photons. By far the most numerous entities around will be photons. And I want to point out two things here about how you measure time. You see, here we have, you see, in present day physics, we have enormously accurate clocks. We have nuclear clocks, atomic clocks, and nuclear clocks. And these all depend ultimately on two very basic principles in physics. That's the two most famous formulae of 20th century physics. There's Einstein's E equals mc squared, and Max Planck's E equals h nu, which I just referred to a short while ago. And if you have any particle then, combining these two, you see it has an energy, and therefore, well, it has a rest mass. If you have a massive particle with a rest mass, and by Einstein that has an energy, therefore, and then by Planck it has, therefore, a frequency. And this is simply governed by these two very fundamental constants of nature, Planck's constant here and the speed of light here. And apart from those two constants, they're basically the same thing. So any particle of mass m is a little clock which oscillates according to very fundamental quantum mechanical laws with a given frequency which is in proportion to the mass. Now, of course, you can't use a single particle for a clock, but basically you have lots and lots of particles and all sorts of complicated physics going on, but the fact that you can make a clock at all is based on the fact that you do have rest mass. If you have no rest mass, then the laws which govern interactions between particles will be either the electromagnetic field, the electromagnetic force, or the Yang-Mills fields which govern the weak and strong interactions. These are all things which are conformally invariant, so they don't actually know anything apart from the light cone. They don't need to know the scale. You see, let's look at the picture underneath. Here we have a couple of clocks. They're meant to be identical clocks ticking away, and here we have the light cone, and here we have the first tick, and the second tick, and the third tick. These bowl-shaped surfaces, these hyperboloid surfaces, represent the units, 1 unit, 2 units, 3 units of time away from that point. And if you have the metric of space-time, this is usually written GAD or d mu or d I j or something like that, this thing that Einstein uses for his theory of general relativity codifies 10 numbers per point. So the metric is 10 numbers for every point. And you need those numbers to tell you how clocks will behave. But what I want to say here is that we only really need 9 of the numbers. That is really the ratios of those 10 numbers, which is what's called the conformal structure of space-time. This is the metric structure. But if you are only interested in this thing called the conformal structure, that is in relativity where the light cones are. It's just the light cones. Remember in my pictures of black holes, the light cones can be There are different arrangements, but where they are is determined by these 9 ratios. The one remaining thing is the crowding of these surfaces here, which give you the remaining component. So when I talk about the conformal geometry, in other words the light cone geometry, that is almost all the space-time geometry, almost in a certain sense, that I only need 9 of the 10 components per point. And massless entities, the photons, they zip along the light cone. They don't make good clocks. They don't make clocks at all, because you can have your photon zipping along here, it never even reaches the first of its surfaces. So it's waiting forever for its first tick. So if you were a photon, you wouldn't be bored at all by this situation. Because eternity is no big deal for a photon. Okay. Various things I want to say about this. One is just a little bit of geometry. When I was talking about the universe here, I tried not to indicate whether it was closed or open or what. It's still a possibility that it might be what's called hyperbolic geometry. Here we have this very nice illustration due to M.C. Escher of what's called the Poincaré disk, which is because I suppose it was used with Beltrami originally. And you find that often the names are not necessarily the right ones. Well, in this case, Poincaré did rediscover it, so I suppose it's not too bad. Beltrami. The trouble with Beltrami is he discovered several different representations of this geometry, about 4 as far as I know. It's a bit hard to label them if you just use his name. This is what may be called the conformal representation. Here we have these fish. I think they're fish. In the middle you can see them, and you can see their eyes are circular. Now this conformal picture, this represents the entire hyperbolic universe that these fish live in. And you have to imagine that these fish, no matter how close they are to the edge, are really just the same. As far as their personal geometry is concerned, they're the same shape and size as the ones in the middle. This boundary represents infinity to the fish. It's handy, you can draw the entire infinite universe, hyperbolic universe, within this entire disk. See, from our Euclidean perspective, we could imagine taking a step outside this, but that wouldn't be respecting the geometry that these animals have inside here. To them, they swim and swim and swim and swim, and they never get any closer to this boundary. Now this trick for representing the entire universe within a finite region is the same sort of trick I'm going to do if I'm talking about light cone geometry, which is the conformal geometry with regard to space-time as opposed to the ordinary space picture that we have here, where we have the light cones as being these characteristic objects. Then we can again use a trick that has been used for many decades now. If you want to talk about infinite things, what happens in the remote future, you can use this trick. That is to say, map your entire universe so that infinity is a finite boundary. So that's what I've done here. And the infinity is squashed down in the same way as in that picture through this finite boundary here. And the photons, which I was saying eternity was no big deal for the photons, they come zipping along like this. As far as they're concerned, this place is just like anywhere else. There's nothing special about infinity, except there isn't anything on the other side. Well, that's what would be special if there wasn't anything on the other side. But you have to bear in mind, I'm going to say something a little bit unusual here, which is maybe there is something on the other side. So this is the extremely remote future. Much now that collapse into black holes, and after, say, 10 to the 90 or maybe 10 to the 100 years, it just gets the pop and so on. Eternity is no time at all for a photon, and photons are interested only in conformal geometry. The Maxwell equations are interested only in the conformal geometry. They are conformally invariant. The way that charges create electromagnetic fields is also conformally invariant. The only thing which is not is the masses of the charged particles. Likewise, the other interactions of physics seem to have the same character. Now, you might have some rogue electrons. I've written this down at the bottom here. See, it's not true that only photons will be around. There might be some massive particles hanging around. A lot of them might annihilate their particles of opposite charge. It might be that the protons